Welcome to this new series about RF and microwave opportunities in education. I'm Pat Hindle, and today I'm talking with Dr. Manos Tentzeris, Ed and Pat Joy, Chair, Professor in Antennas at Georgia Institute of Technology. Welcome, Professor Tentzeris.
Thank you. Good morning to everybody.
So I wanted to learn about opportunities for students who are interested in engineering, especially in the RF and microwave fields. So I thought you would be the best place to start. What are some of the general or 101 courses that Georgia Tech offers for RF and microwave people?
We have a quite large variety of electromagnetic and RF courses. So starting from junior level and introducing fundamentals of electromagnetics, as well as fundamentals of material principles for compis. Pretty much we introduce all students to important high frequency effects. So in the third year, all students get some idea of challenges for high frequency design, high frequency implementation, potential ways to address it, no matter whether they are doubly Comp or CS students. And that's the beginning. Whenever they go to a senior level, we have, I would say, more than 10 classes focused on electromagnetics and RF that are typically attended by any number between 30 and 55 students. So very, very highly attended students, very, very highly attended classes. Despite most of them are electives, I would say routinely, we have to increase the number of students we allow for section due to the high interest. So there are classes in a variety of topics. First one is electromagnetic applications, where we introduce fundamentals of transmission line theory, matching networks, waveguides, circuit parameters, as well as a first get to know with commercial simulators. Then we have a class in a lab on RF engineering design, extending this analysis to active elements. So oscillators, amplifiers, that is accompanied by a lab where students can get a hands-on experience on designing, optimizing, and even measuring a power amplifier, getting exposed to the principles of biasing, isolating specific signals, and customizing the design for practical applications. This one extends in RF engineering too for more systems. Again, senior level, which is now enriched with new applications ranging from opto RF systems, bio RF systems, or smart wearables or flexible electronic topics. Another class we have on antennas and radiation that's also accompanied by a lab discusses different type of antennas, going from low frequencies, for example, for HF RFIDs, going all the way to millimeter wave and sub-terahertz, while also it couples a lot with practical applications like satellite applications, mobile platform applications, coexistence applications. Another opportunity we have is having to do with packaging. Georgia Tech is extremely strong on packaging, and specifically HF and RF packaging. We have had a packaging research center initially supported by NSF, and then we had numerous classes coming out as a result of all our activity there. So we have a packaging class where you address integration issues, you address multi-layer fabrication, address interconnects, as well as mixed signal design and ways to integrate heterogeneous technologies, which is a really hot area nowadays. So lots of students are taking uh, this class. In addition, we have a satellite communication class dealing with anything from CubeSats uh, to different satellite-based communications, especially given now the proliferation of small satellites to enable communication everywhere. That's a very nice topic, combining expertise from different RF and electromagnetics areas. Another class that has been getting continuously increasing interest and still in the senior level group of RF electromagnetic classes is the radar, remote sensing, and in general wireless sensing applications, where we introduce students to different types of radars, continuous wave, FMCW, pulse radars. That's a class where we combine radar principles for radar systems, but also preparing students for radar-based new RF applications, like backscattering applications, or new wireless sensors, or low power electronics, where we discuss ways you can utilize RF and microwave as well as phased array principles to enhance range, performance, and so on. In all these classes, one fundamental component, as I told you, is simulation and modeling. And lately, we have enriched almost all of them with machine learning optimization techniques, preparing future engineers for quick AI machine learning approaches in this case. Now, this is, I would say, the group of strictly EM and RF, but also there is a strong RF component.
That's a lot that you have to offer there. Do you also have graduate courses?
Yeah, we have graduate courses. Before going to graduate courses, I would like to stress like a couple more undergraduate. We recently introduced one is cyber physical systems. Cyber physical systems which more or less combine RF principles with communication principles, smart manufacturing principles, and also digital twins, which is another class that lots of students are taking because it prepares them for future digital twin, industry 4.0, and lots of futuristic applications, 5G plus. And the second class I would like to feature, which is not strictly RF IMAC, but has a strong component, is some bio-RF / opto-RF class, where we combine this in both device level and also network level. And for those interested, there is one class also for low frequency electromagnetics. I know it's not RF. I would like to feature that because lots of people like in space communications, weather monitoring, solar flare monitoring, atmospheric sciences, like taking like this low frequency electromagnetic class. Now for graduate classes, again we have I believe 8 or 9 classes having to do with RF spanning all the way from low frequencies to terahertz. One has to do with RFIC design, which prepares more or less graduate students to for IC design from different steps, from concept, spec definition, simulation, layout optimization, and sometimes even fabbing out and measuring the prototypes. 2 classes on numerical electromagnetics dealing with practical ways of modeling or simulating complicated structures, more or less encompassing the traditional approaches that most of the current simulators use, finite element, finite difference, integral equation, method of moments, but also new AI ML algorithms, starting from KNN or simple ways you may implement utilize in MATLAB, and then going to a more advanced ML algorithms where you need maybe to program yourself, defining cost functions and all this. Couple more classes in graduate curriculum, which has to do with a more advanced fundamental electromagnetics class, where you get into more depth in electromagnetic effects. For example, some novel frequency selective surfaces, reconfigurable intelligent surfaces. What are the major challenges whenever you have flexible or conformal RF devices, how you calibrate them, how you address them in your design to make them to be more rugged. Another class having to do with sensor networks, where we start with design optimization of sensors, and then generalizing for a large number constellation for Internet of Things, or Internet of Everything, as we call it. We have, let me take another look on some complementary ones. We have an advanced class on radio in Earth and space, which allows students to get ready, for example, for plasma environment, solar space weather, navigation, Earth atmosphere. Another class on satellite communication and navigation systems, so utilizing RF and electromagnetics, indoor, outdoor space, underwater navigation, addressing all the challenges of propagation and potentially multiple frequency band utilization. And also, we have a generic microwave design class. And talking about microwave design, pretty much we're talking from all topics from MMIC to different types of nanotechnology-based interconnects, utilizing 2D materials to reduce latency for RF devices, or build stable interconnects, for example, for fiber over RF. So this is a microwave design class, which has also a lab component where you prototype it. So in most of these classes, we have a really extensive additive manufacturing facility, as you already know, which allows students to quickly prototype utilizing inkjet and 3D printing, and then do some measurements pretty much right on the spot. We discuss ways of having students ready for doing the 3D printing or the additive manufacturing, and figuring out, for example, limitations. You know, you could get a very low cost 3D printer, and then you may print RF devices all the way up to 28 gigahertz. And maybe after that, you start having issues. So they're ready to do very quick prototyping this way, taking these classes, and knowing what are the challenges of additive manufacturing, as everybody wants to move to this direction. Now, and that's a very generic overview. There is another graduate class for EM radiation and antennas, talking about novel radiation structures. So reviewing new topologies, reviewing antennas that are extremely broadband. So if you want to design like a 10-to-1, 20-to-1 bandwidth antennas, if you want to integrate with some implantable. So lots of more, I would say, advanced radiation and antenna topics. And there's a class again for cyber physical systems. But this graduate class, in a sense, couples electromagnetics RF to energy systems. So it's focusing, for example, how you can have RF systems to build a digital twin or a safer grid. And what are the special challenges of having RF for a very high power applications? So what are the challenges if you're trying to monitor something in kilowatts, or if you try to integrate something for wireless power transfer? There's lots of discussion nowadays about solar wireless power transfer, or in general wireless power transfer, and building some cyber physical system to monitor this utilizing electromagnetic principles is a big plus, because that's going to be far, that's going to be difficult to do manual inspection due to the high power levels, voltages, and so on. So that's another graduate class. I want to stress, and that's something I believe quite unique, that students here pretty much from the sophomore year, they get involved into practical projects, in research projects in many labs. I mean, in my lab, routinely, I have 5 to 7 undergraduates doing work. So in addition to the traditional senior design project that pretty much exists everywhere, we have this type of early RF research projects, even from sophomore level, and that helps people getting exposed to the multidisciplinarity that every RF engineer of the future will have to resolve. So the idea is, from what I told you, okay, we have a multitude of classes strictly focusing on this, on the topic of EM and RF, but also we have quite a large variety of EM and RF research opportunities for students going all the way from sophomore all the way to PhD students. Just to give you an idea, I mean, pretty much there have been at least, I believe, 5 or 6 startups coming out of undergraduate students who really like the MRF, came with some ideas, and they're willing to pursue them in the form of some companies in this. So that's another, I would say, aspect of this.
Yeah, that's a great variety of courses, and I know you guys are very well known for your additive manufacturing research, and it's great that you have practical ways for students to actually, make devices and measure them. I think that's kind of invaluable. So how would you suggest that, students, maybe high school students, best prepare for this type of degree?
Are we talking in terms of admission or in terms of knowledge required? Because
Uh,
actually, high school
Knowledge and
students,
courses, yeah.
it's quite interesting because this semester we hosted one high school student from 11th grade, and we may host a couple more next year. So advice number one: get involved. That means if you have a strong interest in the area of wireless technologies, RF applications, don't be afraid to contact some professor in a university nearby you, even if you are like in 9th grade, 10th grade, 11th grade. Right now, with the 3D printing, which is some expertise pretty much very well available to lots of high school students, you are going to be able to contribute, even just prototyping and modeling. So number one, don't be afraid to get involved. With additive manufacturing, you can start doing stuff very, very early. Number two, try to focus on the principles and not the equations. Now, I know that lots of students are afraid of RF and EM because they consider it to be something really abstract, full of
Heavy math.
equations. Exactly. They think it's math. And actually, with all the availability of the commercial tools we have now, you can get a pretty good feeling of all these effects without needing to resort to the solution of really complicated equations. So don't be afraid of this topic. Get some physics classes that will allow you to get a good understanding of the principles and a good feeling of what you will have to come across in a career like this. And you will see that getting into this field is actually very exciting. And it's very exciting because that correlates to pretty much everything in your everyday life, ranging from a cell phone, an iPad, Internet of Things, sensors. That's a very exciting field. So don't be afraid of this. You will see that even if you start building some foundation with some good physics classes, that's going to be very, very helpful. And the advice number three is get familiar with tools. You refer to 3D printing, you refer to additive manufacturing. No matter how complicated it is, or no matter how expensive it is. I mean, you can buy pretty much a printer now from your local Best Buy for like what, like $400, $500, and then you can go back home and you can start printing antennas, simple circuits. They're small robots. I mean, sometimes I'm going to the elementary of my daughters, and they have started doing robots like from fourth or fifth grade. So it's not a tough job. Engineering is quite an exciting job. That will give you a better understanding of the world, but also that will prepare you to do great things in the future. I mean, think about what a ref has enabled us to do nowadays. Think about the cell phones in the early 2000s and right now. We have this pretty much smart computer in our hands or even in our watch. I mean, the future will have virtual reality, enhanced reality, autonomous cars, pretty much robots everywhere, wireless sensors. So that's a very exciting field. And getting involved, even getting familiar with some of these systems and learning the principles they operate, how your phone works, or how a robot can be controlled, how it can communicate, will help you a lot getting ready to study in this field. So I would say if you do that, then you have a great chance to be a very successful RF engineer. I mean, this is my generic advice. I would be very happy to talk to your listeners for more information or even hook them up with some high school students that have spent time in our lab. And I will be happy to provide more advice on this.
Awesome. I love it. Get involved. It's good advice for everybody.
Definitely.
So thank you, Professor Tentzeris, for talking with me today. Great opportunities for engineering students, and it's an exciting field in RF and microwave engineering. So I encourage everybody to check it out and pursue it if you like it. So it's
Great.
been great learning about Georgia Tech. You have so much to offer, and one of the top universities for sure in the U.S., if not worldwide. So to our audience, you can find more videos at videos.microwavejournal.com. Give us a like, and thanks for watching.